if you want to see, let's see, if you want to see, what was it? Rectangular, rect to polar, we can see these. Let's pretend for a second we have nothing. I only give you an x and a y direction. I say something like, hey, deal with this, -17, comma 14. Turn that into polar notation. Okay, thanks, Mr. Botzer. Here's how you can do it. It's not that bad. You know this is an x amount. You know this is a y amount. So make a little origin. Done. Go that amount in the x direction. And it doesn't have to be to scale. You're just kind of scratching this real quick. So at the origin, and I go -17, negative direction. Then go 14 from here in the y. So this is head-tail method. That's 14. Like all good vectors, we go start to finish. In order to get polar notation, remember, polar notation is the size, comma, angle. You can get the size of this hypotenuse, because this is a right triangle, by just using the Pythagorean theorem. Remember, Pythagorean theorem, when you learn it in your math classes, looks kind of like this. If this is side A, B, and C, it reads a squared plus b squared equals c squared. Or if you're solving for c, you could say c equals the square root of a squared plus b squared. Since we're generically using vectors, this could be a displacement, a velocity, an acceleration. Later on in the year, we'll see it could be momentum. It could be a force. We'll see a bunch of stuff it could be, but it's just a vector. Okay? This is kind of what you've seen in the projectile stuff we did the past 3 days. But if I wanted to solve for the length in this problem, I could just take and note I'm going to ignore the negatives here because those negatives are going to become squared, so they're going to become a positive because a negative times a negative is a positive. So what I can do is I can just say 14 squared plus 17 squared. Take the square root of that, and that is my hypotenuse. Whenever I do this on my calculator real quick, I throw in 14 squared, I get 196, 17 squared, 289, so the square root of 196 plus 289 equals my hypotenuse. 289 plus 196 equals the root of 485, which is 22. That equals C. So for my polar notation, my size for it is 22. Now I just need to get an angle. Well, looking at the triangle that I have right here, the angle I can easily get is this angle right here. That's not the polar angle, but it's an angle I have access to. If I have this angle that I can easily get, well, I can get it with an inverse function or an arc function. Labeling my triangle, this is the opposite side. This is the hypotenuse I just found. This leaves the adjacent. What I can end up saying is, since I have an opposite and adjacent, I can say that theta equals the inverse tangent or arctan of, and with TOA, SOHCAHTOA, TOA, that's TOA, it's opposite over adjacent. 14 over 17. I've ignored the negatives here. The negatives actually aren't going to help me at all. I'm just looking for what this angle is on the inside, and to do that, I just need the positive values. We'll figure out what that angle means in a second. So if I do the inverse tangent of 14 divided by 17, opposite over adjacent, I find that the angle there is 39.5 degrees. So this is 39.5 degrees. Okay. But, like all good things, this never ends. That's not the angle I want. The angle you want for polar, and this is where on everybody's test I wrote, draw a triangle. You want it from the positive x-axis over to here. Now the easy way to do this is to recognize that if you went a full 180 degrees, if you made the whole loop, that's 180. But then you pulled back from it 39.5. So if you do 180 minus 39.5, because you didn't go all the way, you would get 140.5 degrees. And that is your polar angle. So we have in the end our size, 22, as given by a Pythagorean theorem, and our angle, we used an arctangent, or an inverse tangent, to find the angle of our triangle, but the angle of the triangle isn't what we wanted. We wanted the polar angle, which we found by noting that going halfway around is 180, and then backing off from that by the 39.5 gave us 140.5. And this is our polar. So that's how you do polar there, Austin. I'll just leave that sit there.